This is another problem from Chapter 5.1. This is problem number 36, and I've chosen this problem to illustrate an exponential function that has a negative exponent, and therefore this is going to be something that is a decreasing function, and this is a radioactive decay function. Let me read you the problem. Let me get my calculator a little bit bigger here. It says a breeder reactor converts stable uranium-238 into the isotope plutonium-239. The decay of this isotope is given by A of t is equal to 100 e raised to the negative 0.00002876 t, where A of t is the amount of the isotope at time t in years, and 100 grams is the original amount. We want to find how many grams remain after 100 years. Well, to do this, see, I'm going to move it over here. Hopefully I can, nope, I'm not going to quite get everything I need. I'm going to make the calculator slightly smaller. And now we can maybe just fit everything in here. All right, just fits. All right, here we go. To do this, we'll turn on the calculator, and let me clear out what I had in here before, because we're not going to need any of this. Okay. Back to the beginning here, clearing that out. What we're going to have is we're going to put this in the calculator. So after 100 years, that's when the t is equal to 100. So I'm going to take my function here. If you can read up here, I'm going to have this 100e raised to the, and this is my function. So let's put that in. So I'm going to have 100. Then using the exponential function e raised to the, we have to make sure we get our negative point. 1, 2, 3, 4 zeros, and then 2876. And we can't use, I'm going to use t equal to 100, so I'm going to have times 100. And now closing our parentheses, we'll get an answer. So our answer for this one, and let me set up my pointer. Our answer for this problem is going to be the following. We're going to have that, we're going to just have 99.7 approximately grams. Now notice that almost the entire 100 grams is still there after 100 years, and so this decays very, very slowly, and we can see that from over here when we look at our pointer over here. This is a very, very small number, and it's negative, so it is decreasing, and that answers part A. For part B, we want to graph this function, so I'm going to go into the calculator and put in this function. So I'm going to have 100, then we're going to have our exponential function e raised to, then I'm going to have negative 0.00002876. And we have to use x no matter what it says. Wrong thing here. Let's see if I can go. I hit the wrong button here. I can't read my calculator very well on the screen here. So let's clear this out here. Okay, now I put in the x, close the parentheses. Now before I graph this, let's set up our window. We want to go from 0 to 500,000. So I have the 0. So now I have to have not 550,000. One more 0 here. And let's use a scale of, say, 5,000. That'll give me 10 tick marks horizontally. My y minimum, let's just make this 0. And this thing, our y maximum, is what we started out with. That's 100. And let's make this scale 0 as well. So hopefully you can see how I've chosen my x values. That's equivalent to the time. That's going to be from 0 to 50,000 years. And my y is how many grams I have left, and that went from 100 to 0, and so from 0 to 100. Now we can look at this graph, and here is the radioactive decay. And so that gives us a decent graph, and so this would then complete part B. For part C, it says the half-life is the time it takes for half of the initial amount to decay. We want to use graphical methods to estimate the half-life of this isotope. Let's look at a trace of this function. Now, to get a half-life, what we really want is we want this Y value to be half of the original 100, so that needs to be about 50. If I back it up a little bit here, we're seeing that it's somewhere between this 23,936 and another value here. Okay? Now, we can get a better estimate using other techniques. I could zoom in and try to get closer, but what I'm going to do instead is I'm going to go in here and put in these 50 here. Oops, I want one too many. So I need to do 50. Let me just delete. Okay, now I have it. Now if I graph that line, what we can do using our graphical techniques, if I go into the Calc menu and choose number 5 here for intersect, and my first curve is the Y1 curve, my second curve is the Y2 curve, and entering we have an answer of, here we got 2,500, excuse me, 25,000. So our answer for this one, the half-life for this is going to be about 25,000 years. And my pen's not doing too good, but anyway, so this is going to be this many years is the half-life for plutonium-239. This finishes this problem, and this is an example of radioactive decay using graphical techniques to solve problems.